I'll be talking about the AdS CFT correspondence that was introduced in the previous lecture. And I will talk about this basic specific example of the equivalence between n-equal four supersymmetric Young-Mills theory and string theory in AdS 5 crosses 5. So it turns out that these theories, well, they are equivalent to one another, so they just describe the same physics in different ways. They possess a hidden symmetry that turns out to be very useful and in fact allows to, well, almost solve them exactly. So these two theories, especially this theory, seems to provide an example of four-dimensional quantum field theory that's exactly solvable in the large n limit. This hidden symmetry is called integrability, and on the string side, it's basically a manifest theory symmetry of the Lagrangian, whereas in n-equal 4 super Young-Mills, it's a hidden symmetry. And one has to really keep only planar diagrams to see it. So part of my lectures will be to derive how this symmetry or how integrability arises in this particular quantum field theory in the larger limit. Here is the plan of the lectures. So first I will just very briefly describe the features of the AdS CFT correspondence that I will need later. Then I will tell how the problem of finding the spectrum of n-equal 4 super Young-Mills can be reformulated as in terms of diagonalizing some spin chain Hamiltonian. And this spin chain Hamiltonian turns out to be integrable. Now, in integrable systems, there is a rather well-developed theory how to exactly solve both classical and quantum integrable systems. The main method was proposed by Bethe 70 years ago, and it's called Bethe ansatz. So I will tell you about Bethe ansatz and introduce the methods that are used there. Also, I'll talk about string theory in AdS 5 crosses 5, and basically about classical string theory. And also, if there will be some time left, I'll describe the algebraic formulation of Bethe ansatz that uses certain mathematical concepts useful in integrable systems. So first, how these theories are defined. Well, strings are propagated in a 10-dimensional background that's product of anti-de Sitter space and the sphere. And anti-de Sitter space has this metric. So it's basically a Minkowski space-time with an additional coordinate z, and the metric is curved in the z direction. I'm sure you'll see this formula many times in this course of lectures. So a cartoon of this space is that it's sort of an upper half plane. So there is foliated by Minkowski space-time. So here are the spatial or normal Minkowski directions and an extra coordinate z that runs from 0 to infinity. And so the space naturally has a boundary. The metric has a double pole at the boundary. So it's sort of singular in that near z equals 0. Now the cartoon that's usually drawn is respect to this correspondence is that gauge fields live on this boundary. So they live on the extreme of this space. Which is just a 4-dimensional Minkowski spacetime. But strings are allowed to propagate in the bulk. So they can start at the boundary and expand in the bulk. So strings live everywhere in 10-dimensional space. So I'll return back to formulation of the string theory. And the bosonic part is, well, the Lagrangian for the string is just Nabogot or Polyakov action, and the bosonic part of it is easy to write down once you know the metric. There are some difficulties or coupling fermions in this background is a non-trivial problem because there is also a flux of the Ramon-Ramon field. And fermions coupled to that. It requires some work to understand how the sigma model action looks like in this background. So as Mukund told you, there are two parameters that characterize string theory in this background. So one is the string coupling. It basically describes the probability for strings to split and join. And in what follows, I will take this coupling to be strictly 0. So we'll consider strings that that do not interact with one another, but still they are allowed to fluctuate. And so the problem is intrinsically quantum mechanical. The parameter that governs the fluctuations of the string wall sheet is the string tension. And here, since the metric is chosen to be dimensionless in these units, the string tension is also dimensionless. So this is because here we put radius of AdS to be equal to 1. And for consistency, we should also put the radius of S5 to be 1. So we measure everything in the units of the radius. So then there is also the string tension, which can be thought of the ratio of radius squared to 2 pi alpha prime. Now n equal 4 Super-Yang-Mills theory is a gauge theory in 4 dimensions, which has a maximal number of supersymmetries a non-gravitational theory in 4 dimensions can have. So in a supersymmetric theory, so that there are supercharges that are symmetries of that commute with the Hamiltonian, and a supercharge is a two-component Weyl spinor. And in principle, it can have another index, so there can be several supercharges. So n equal 4 means that there are exactly 4 of these supercharges, so A runs from 1 to 4. And just from representation theory of the superalgebra, it follows that this is the maximal allowed amount of supersymmetries. So for that reason, the n equal 4 superrank-Mills is very rigid theory. The field content and the Lagrangian are fixed by supersymmetries. So if you require that the action contains only operators of dimension 4 and less, then the action is unique. Now the simplest way to construct it, to construct the Lagrangian, is to start from 10 dimensions. Well, why from 10? One simple explanation is that the number of independent components, the number of independent supercharges here is equal to 4. And then if you count 2 independent Lorentz components, it gives 8. And also supercharges are complex, as Weyl spinors in 4 dimensions are complex. So we should multiply by 2 again. So this gives 16 real supercharges. So supercharge in n equal 4 superrank-Mills has 16 independent real components. And this is precisely the dimension of my Rano-Weyl representation in 10 dimensions. So in 10 dimensions, Dirac spinor has 32 components, 2 to the 5. If we impose the condition that it's left chiral, then the number of independent components is 16. And in 10 dimension, Weyl spinor can also be real. So my Rano-Weyl spinor will have 16 components. So if we start with a theory in 10 dimensions that has normal n equal 1 supersymmetry, and then reduces to 4 dimensions, we will get the action that will have the desired properties. So we start with n equal 1 superrank-Mills in 10 dimensions. This Lagrangian is so it has a very, very simple form of Young-Mills field interacting minimally with my Rano-Weyl fermions. So psi here is 10-dimensional my Rano-Weyl fermion. So it's real and satisfies the constraint with gamma 11. It's a unit, it's an eigenspinor of gamma 11. So we'll take the gauge group to be UN or SUN. So at the end, we'll take the large n limit, so it will not matter if it's UN or SUN. Which means that both A mu and psi are n cross n Hermitian matrices. Now, the dimensional reduction means that we treat 4 directions and perpendicular 6 directions differently. So we write that decompose so 10-dimensional space in 4 plus 6 way, so that 10-dimensional index that runs from 0 to 9 becomes decomposed into a 4-dimensional index and additional 6 indices that we'll denote by Latin letters. And we declare that, so we take this Lagrangian, decompose fields according to this 4 plus 6 decomposition, and declare that they only depend on the first 4 coordinates. Or in other words, in the Lagrangian, we just put all transverse derivatives to 0. And so this way we get a Lagrangian that lives for a field theory in 4 dimensions. But since in 10 dimensions it had one supersymmetry with 16 component supercharges, it will have n equal 4 supersymmetry in 4 dimensions. So of course the original 10-dimensional Lorentz invariance is broken by this procedure to product of 4-dimensional Lorentz symmetry and SO6 rotation that act on the 6 indices. So this SO6 survives as a global symmetry of n equal 4 super-Young Mills, and usually this symmetry is referred to as R symmetry. So the first at first, we might think that this is the global symmetry of n equal 4 super-Young Mills. So this is, at least this is the symmetry that's manifest from the Lagrangian. You will see that the real global symmetry is a little bit bigger, but to begin with, it contains also supersymmetries. And actually, the bosonic symmetry is a little larger. So the fields are then decomposed into 4-dimensional gauge fields. But now 10-dimensional gauge field has 10 components, so 6 of them become scalars in 4 dimension. So there we will have 4 scalars. Oh, sorry, 6 additional scalars. And obviously, the scalars transform as a vector of SO6. So they have a vector index of R symmetry. Now, spinors decompose into 4 complex wheel spinors in 4 dimensions, and their conjugates. So this extra index is an SO6 spinor index.
I'm sorry,
Or n.
N is
Yeah,
the UN.
of UN, yes.
Okay.
So these fields are just matrices, so they remain n by n matrices with color indices. So in particular, these fields phi, psi, and psi bar are in the adjoint of of UN, and we only so the decomposition only concerns the Lorentz indices. So we basically decompose the Lorentz index into the four-dimensional part and perpendicular part. Plug it in the Lagrangian, forget about derivatives in the 6 dimensions, and we get four-dimensional action. So the Lagrangian that we get in this way is a little bit more complicated than 10-dimensional Lagrangian. Of course, it contains f mu squared, but then so the field tensor in 10 dimensions has okay, so these are just 4 cross 4 components of the field tensor, but it also has 4 cross 6 components and 6 cross 6 components. So 4 cross 6 components become the kinetic term for scalar fields, and 6 cross 6 components describe quartic interactions among them. So this is a very specific form of scalar-scalar interaction that is prescribed by supersymmetry. So the action, this action is unique in the sense that we cannot adjust any coefficient here. That would break supersymmetry. And then there is also interactions with fermions. So fermions interact in the minimal way with the gauge fields. And they also contain Yukawa interactions with scalars. So these commutators here are remnants of covariant derivatives in 10 dimensions. So covariant derivative contains a commutator. Once we forget about the normal derivative part, the commutator what's left. Okay, so this is the Lagrangian of a four-dimensional field theory of n = 4 superrank Mills. Sometimes it's useful to generalize this procedure to arbitrary number of dimensions, mostly for, okay, so one of the reasons is that this continuation to arbitrary number of dimensions gives a convenient regularization scheme that's called dimensional reduction. So if we say that mu runs from 0 to d minus 1, and I runs from 1 to 10 minus d. And take d to be 4 minus epsilon, then this defines a regularization scheme called dimensional reduction. So as you know, when we do quantum calculations in four-dimensional field theories, we often encounter divergences, infrared and ultraviolet. And one convenient way to treat both types of divergences is to shift a little bit from 4 dimensions, because in theories in less number of dimensions, ultraviolet divergences are weaker, so the theory behaves better on short distances. And in larger number of dimensions, field theory behaves better at large distances. So if you keep epsilon as a parameter, we can basically calculate any diagram without divergences. But of course, if you go back to 4 dimensions, we encounter poles in 1 over epsilon. So this is the usual dimensional regularization method. Now, if we apply it for a supersymmetric field theory, it will for sure break supersymmetry. Just in the naive way, if we do momentum integration in 4 minus epsilon dimensions. Why? The reason is that in arbitrary number of dimensions, the number of, say, scalar components in the multiplet changes with dimension. And so if we don't take it into account, regularization will break supersymmetry. So this regularization, by definition, preserves n equal 4 supersymmetry, n equal 4 supersymmetry in any number of dimensions. So it's a way to supersymmetrically regularize the theory. Yes?
You said that the point of n equal 4 super n0 is a conformal invariant. That means that n equal 1 conformal theory is also has a conformal invariance, that the one 10 dimension?
No. No. That's
So
not
how
true.
is that?
Because scaling transformation act differently in different dimensions. So if you shift from 10 dimensions, for instance, the coupling constant, so the Lagrangian should have dimension d in d dimensions because the action should be dimensionless, which means that the coupling constant, and the action is made of operators of dimension 4. This means that the coupling constant has dimension 4 minus d. So if in 10 dimensions, for instance, it will have dimension minus 6. So there will, in any dimension except for 4, the gauge theory from the beginning has a mass parameter in terms of its coupling constant. So it's a property of only 4-dimensional gauge theories that they have no mass scale classically, and it can only be generated dynamically through dimensional transmutation.
Excuse me.
Yes.
Yeah. The last thing that you could you just repeat the last thing that you said about this regularization scheme not breaking the supersymmetries? I didn't quite get it. I mean, you said that the general scheme would break supersymmetries.
Yes.
How does one see that? I mean, this particular scheme doesn't break it.
Because we start from 10-dimensional supersymmetric theory with 16 supersymmetries.
Right.
And when we do this reduction, we keep all the supersymmetries, right? Because we don't do anything to the field content. We just say that some fields don't depend on certain directions in 10-dimensional space-time. So supersymmetries act as if they were acting in 10 dimensions. So it is uniformly supersymmetric in any number of dimensions. For instance, if you take d to be 2, we will get n equal 8 two-dimensional supersymmetric Yang-Mills theory. If we put d equals 6, we will get supersymmetric 6-dimensional theory, and so on. Now, the difference to the usual dimensional regularization scheme is that we change, so the number of scalars changes with dimension. So this index I runs from 1 to 10 minus d So it depends on epsilon. If you shift by the number of dimensions by epsilon, the number of scalars should be also corrected. Okay, so this Lagrangian contains only one parameter, which is dimensionless in 4 dimensions, the gauge coupling. Now, unlike many other gauge theories, this coupling doesn't run. So if we compute quantum corrections, we do not need counter terms in the action. And therefore, there is no scale dependence in the coupling. It's just a number that we can take to be large or small. So it's just parameter that we can use to define our theory. Now, string theory has 2 parameters, but as Mukund explained you, there is another hidden parameter here, which is the size of the gauge group. So we should also regard n as a parameter. And then the number of parameters is 2. And these 2 parameters are conveniently chosen to be that Hooft coupling and 1 over n. So if you take n to infinity, then we are left with only planar diagrams. Okay, so for n very large, 1 over n is sort of a continuous parameter. As a matter of fact, it's an interesting question to see that on the string side, n is also discrete. So it's not a continuous variable there. So strictly speaking, in both theories, because the AdS space contains, AdS 5 process 5 contains n units of Ramon-Ramon flux, and direct quantization, for instance, for the flux through the sphere, tells us that the flux should be integer valued, total flux, and this happens to be n. If we identified parameters on both sides of the AdS CFT correspondence. So it's just direct quantization condition for the flux. Okay, so super n means contains 2 parameters, which is gm squared times n and 1 over n. And then if you consider, say, correlation functions of single trace operators, so this can be products of local fields, Wilson loops, whatever. If you count the color factors of this in the Feynman diagrams that contribute to this correlator, you have seen in the previous lecture that this can be written as a double series. So it will be given by summation in the powers of 1 over n squared with the coefficients that are functions of only the Hooft coupling. And, well, in perturbation theory, we expand these functions in lambda. Now, topologically, these are given by diagrams that are triangulations of Riemann surfaces of genus G with n holes. So each operator produces a hole in this surface. So the number, okay, so the power of n then counts the number of handles on this surface and together with the number of holes. And this already smells like string theory. So topologically, it's the same as the diagram that we would compute for finding the string amplitude with n vertex operators with 1 over n squared associated with the with 1 over n associated with the string coupling. So even at the superficial level, not going into the details of the AdS CFT correspondence, which is the exact equivalence, we can anticipate that local operators, or actually any operators, but so local single trace operators should be in one-to-one correspondence with vertex operators of the string, and vertex operators define as the spectrum of string theory, so there are as many vertex operators as there are string states. So so we expect that local gauge invariant operators are in one-to-one correspondence with possible string states in the AdS 5 x 5 background. So finding the set of operators is the same as finding the spectrum of string theory in AdS 5 x 5. And at first it sounds that this is a very simple problem on the left-hand side and a very complicated problem on the right-hand side. Because to finding the string spectrum, we should take, I don't know, the string Hamiltonian and diagonalize it. And this is equivalent to solving the two-dimensional sigma model that describes propagation of the string world sheet in AdS 5 x 5. So the problem is as complicated as solving a two-dimensional interacting quantum field theory. So it's not very simple. But on the left-hand side in Young-Mills theory, it seems that this is a purely combinatorial problem. So we just list all possible local fields, phi, a mu, psi, make gauge invariant combinations of them, multiply at the same point, take the trace, and this would give us the spectrum of operators. It turns out that once we switch interactions, the picture becomes a little bit more complicated, and in fact it's also amounts in diagonalizing certain Hamiltonian. Before constructing this Hamiltonian, I would like to say a few words about the conformal symmetry that plays an important role in this particular instance of the AdS CFT correspondence. So for that, okay, so let me first say tell you how the parameters. Yes.
You started with n-dimensional theory, but it was a Zarembo's theory, yeah? There was
yes.
no gravity. And what changes if you include the gravity? Start with gravity.
In principle, yes. One can do dimensional reduction in supergravity as well. It's also depends on what you want to achieve. So this was just a trick to get the action. In fact, this way of writing down the action with 10-dimensional Dirac matrices is most convenient for practical calculations. If you ever need to compute a diagram in n equal 4 super Young-Mills, it's the best way is to use these 10-dimensional notations. So so the AdS CFT correspondence tells us that the string tension of the string is equal to square root of the Hooft coupling divided by 2 pi. And the string coupling is lambda divided by 4 pi n. So I guess Mukund will explain you why, how to get this precise identification of couplings. But let me just consider it as given and see what kind of limits we can take. So one obvious limit on the string side is to send GS to 0. While keeping tension fixed. So this corresponds to considering free strings. Let's see what does it correspond to on the superrank Mills side. Well, the string tension depends on the Hooft coupling, so we should keep lambda fixed. But GS contains 1 over n, so this limit amounts in taking n to infinity, and this is precisely that Hooft's planar limit. So in all this sum over various diagrams of various topology, we keep the lowest possible one for the surfaces which can be drawn without self-intersections on the surface without handles, so actually on the plane. So according to AdS CFT, this should be equivalent. Now, and this is the limit I will always consider. So from now on, n will be equal to infinity and GS will be equal to 0. But we still have one parameter, which is the Hooft coupling, and it's in our hands to make it big or small. On the string side, a natural thing to do is to make tension big. So then the string becomes sort of rigid. So it's very, it costs a lot of energy to make it moving. So basically, it suppresses all kinds of fluctuations. So it corresponds to classical strings that do not fluctuate. Now, if you look at superrank Mills, then since tension is proportional to the square root of the Hooft coupling, to make tension large, we should make lambda large. And this is a very unusual limit for a field theory, so it corresponds to the strongly coupled, to strong coupling limit. So now we should be able to understand what how classical string behave even in this curved background. So in this sense, we completely understand what happens in this strong coupling limit of the superrank Mills theory. And I think this is a great achievement, that just by looking at weakly coupled weakly coupled string theory, we are able to quantitatively describe what happens in a strong coupling limit of a field theory. And actually, what makes it even more interesting is that this is basically the gravitational limit of string theory. So the strong coupling limit of the gauge theory maps into the classical gravity limit of strings. Now the opposite limit, where we do understand quantitatively Superang-Mills theory, which is the weak coupling, corresponds to the limit when tension is very small. And this is very hard to understand because strings become very quantum in this regime, and since they propagate in the curved background, it's hard to understand what goes on. Geometrically, one can think of taking the limit when the curvature becomes very large, because we measure. So remember that the tension is the radius, is the ratio. Okay, it's measured in the units where the radius of curvature is 1. So it's the ratio of the radius to alpha prime. So if we instead keep alpha prime fixed and take radius to 0, then this would correspond to tension going to 0. So this tensionless limit is when the geometry becomes very singular, so the sphere shrinks to a point, and the AdS space actually becomes a sort of a cone. So when the curvatures are very large, we in general don't know much about string theory. So it's a quantum, very quantum limit, and well, the string description is not that useful, or is not that simple in this limit. So these CFT correspondence also identify observables. In both theories. And there are basically two kinds of observables in Superang-Mills theory. So one is possible observable is the Wilson loop. It's a non-local operator that depends on the contour. So it is a contour observable. In perturbation theory, it's given by a sum of diagrams, and if we take the large n limit, these are basically planar diagrams on a disk. So there is a contour that can emit gluons. there's, let's see, this type of diagrams are not allowed. Okay, so the diagrams that correspond to the calculation of the Wilson loop correspond to triangulations of a disk. And on the string side, accordingly, we have the string well sheet. So we should sum over the string well sheet that have this contour as a boundary. So we should draw this contour C on the boundary of anti-de Sitter space and sum overall surfaces that extend in the bulk and end on this contour. So to calculate this, the expectation value of the contour of this contour observable in string theory, we should average over all contours, over all string well sheets with prescribed boundary conditions. And the weight is basically the string action. And since the tension is proportional to square root of lambda, okay, so this coefficient that stands here is the string tension. So if we take it to infinity, then this integral will be of saddle point type. So the action will be very large, and it will be dominated by the classical configuration, and the classical configuration is just the minimal surface with the prescribed boundary. So its strong coupling Wilson loops satisfy the area law. Now, in fact, this prescription has to require some regularization. One can show that this minimal area is regularized minimal area is always negative. So Wilson loop is the exponential of some with positive exponent. And if one looks a little bit more into the details of the field theory calculations, then one can see that it fits well with perturbation theory. So perturbation theory also describes sort of growth of this expectation value with decoupling. Now, another type of observables is local operators. Actually, when I'm supposed to finish? Quarter to.
I have a question. It's probably not very important for what you are saying. So on the Young-Mills side, you said that the Wilson loop can be divided, can be triangulated when the scalar term is present with the absolute value of x dot. It's not obvious that, right, when you divide the whole loop into smaller contours, the contributions will cancel.
Well, it's
along the edges.
the role of this term is to regularize the ultraviolet divergences. So if we calculate, for instance, this diagram, So that would be equal to integral ds prime. Then we insert the propagator, which is something like 8 pi squared x of s minus x of s prime squared, right? And then, so the denominator is the same for gluons and for scalars, but they couple differently to the contour. So the gluon couples with the vector coupling, and the scalar couples with the scalar coupling. So, and the scalar also couples with the I, so the sign, the relative sign here is minus. And that's important because if you like take only this term, only the vector term, like in QCD, then the average would diverge when s comes close to s prime. So this is x of s, x of s prime. So the contour diverges, and it diverges linearly. So there is a linear perimeter divergence of Wilson averages in QCD. But in super-young Mills, this divergence is cancelled by the scalar coupling. So if this is the contour and 2 points come close to one another, then the difference between the vector coupling and the scalar coupling disappears, and these terms nearly cancel. So this leads to cancellations of the divergence. So this expectation value is completely finite. It doesn't require any regularization.
No, I understand when you understand this line as a propagator, you're saying it's right. If I was just thinking of dividing the Wilson loop into smaller loops and expecting to find the cancellations between the contours in the middle going in the opposite direction, right, that you can open a larger Wilson
Yes.
loop into two smaller ones, right,
Oh,
and
I
find
see.
that there is a cancellation between the two parts which are going in the opposite directions.
Ah,
It immediately applies to the gauge
Yeah, yeah, yeah,
part,
yes.
does not apply to the scalar.
sorry, I misunderstood your question. Yes, there is, so this backtracking property is absent for these Wilson loops. Unlike usual Wilson loops in, say, pure young Mills. Yes, this is absent, and I believe also for a good reason. So, if you do strong coupling calculation, you sort of see it. Okay. If there are no further questions, I will proceed with local operators. So, so for local operators, so here for Wilson loops we have a prescription that supposedly works for any coupling. So once we know how to define the string path integral, at least there is a prescription to calculate Wilson loops at any given accuracy using string theory. For local operators, that's not the case. I don't think there is even a prescription how to do calculations at intermediate couplings. But it is known how to do it at strong coupling. So to calculate the correlation function of operators inserted in various points, one first need to calculate the action of supergravity with certain boundary conditions on supergravity fields. So which depend on z and on x. And when they approach the boundary, so they do it in a power-like way with z, and the coefficient in front of this leading power is the source, is what we'll call the source. So then computing it for arbitrary sources and taking variational derivative, we should get the correlation function. So this is a prescription to calculate it. As I said, there is no string prescription to do it. So this prescription is given in terms of supergravity is only approximation to string theory, low energy approximation. And it's only valid at strong coupling. Now, the only exception for which we know how to define a correlation function of local operators using string theory is a two-point function. So this relies heavily on the conformal symmetry. So the goal of the rest of my lectures will be to understand the two-point functions at intermediate coupling. And this is actually the same as understanding the spectrum of the theory. Actually, it will be convenient for me to stop here. Yes.
You're talking always about local operators. There are no non-local or global observables in N equals 4 to 10?
Well, basically, the Wilson loop is a non-local observable. Now, of course, local operators form a complete set of operators. So in principle, if you have some complicated non-local observable, it can be expanded in local observables. So Wilson loop can be written as an expansion in terms of local operators, an infinite expansion. So OPE, usual OPE stuff. And the Wilson loops also form a complete set of observables. So any operator can be expressed in terms of Wilson loops. So they're mutually complementary. Yes.
So since you, well, I mean, the theory has this supersymmetry, I expect that part of the spectrum you can say something. Maybe they are protected by the symmetry, or
Oh yes, of course. There is.
so you are saying something which is not protected by.
Yeah. So the goal will be to understand the non-protected stuff. Yes.
So you said just now that with the local operators there wasn't a prescription for computing them in the string theory, and then you also said that the Wilson loops form a complete basis of operators.
Yes.
And then you gave a way to compute the Wilson loops in the string theory.
Oh, yeah. So right. So I see there is some logical contradiction here. In principle, one could start with Wilson loops, shrink them to points, and that would give a prescription to compute local operators. But this is kind of complicated. So, I mean, there should be some better prescription, like taking string partition function on the sphere, inserting some vertex operators, and that would give immediately give an amplitude for the correlation function. Such prescription is not known.
Any more questions? And Costa, and go for lunch.